In the previous video, we studied the transverse magnetic modes or transverse magnetic surface wave modes in a grounded dielectric slab. Now, in this video, we are going to extend our study to the transverse electric surface wave modes in grounded dielectric slab. In a similar way to the previous video, for the case of the transverse electric modes, we are talking about Ez equals 0, but Hz equal Hz as a function of x and y multiplied by the propagation constant e to the power minus j beta z. And as we said, we have two Helmholtz wave equations, one inside the dielectric medium and one inside the free space. The one inside the dielectric medium is partial by partial x squared plus kc squared hz, and in the outside medium it is partial by partial x squared minus h squared hz, where kc squared equals epsilon r k naught squared minus beta squared, and h squared equals beta squared minus k naught squared. And as we said, the field dependence on y is constant, so the derivative with respect to y would be 0. And we said that the solution of such Helmholtz wave equation would be inside the dielectric slab a sine kcx plus b cosine kcx. Outside the dielectric slab would be c e to the power hx plus d e to the power minus hx. Now we are going to apply the boundary conditions to determine the unknown coefficients a, b, c, and d. The boundary condition, at the beginning we have the tangential electric field at x equals 0 should be 0, or the tangential electric field at the ground plane should be 0. The tangential electric field in the present case is Ey, and Ey is related to Hz as Ey equals j omega mu over kc squared partial Hz by partial x. So we are going to differentiate the first equation, because this first equation for x greater than 0, greater than or equal 0, and less than or equal d. So we are interested at this equation now. The derivative of Hz with respect to x would be a kc cosine kcx plus, minus b kc sine kcx. At x equals 0, the term related to the value of b is already 0, and the term related to a would be multiplied by 1. And to satisfy that Ey equals 0 at x equals 0, the value of a must be 0. So the value of a is 0. And in a similar way to the transverse magnetic case, we are going to apply the radiation condition that the magnetic field at infinity, at x equal infinity, should be finite or 0. So in this case, the exponential term e to the power positive hx must be multiplied by 0. So the coefficient c in this case, it would be 0. So the remaining parts are hz equals b cosine kcx for x is greater than or equal 0, and x is less than or equal d, and hz equals d multiplied by e to the power minus hx for x is greater than d. By applying the boundary conditions at the interface between the air and the dielectric medium, the tangential magnetic field at x equal d equals the tangential magnetic field at x equal d inside here. So the tangential electric field inside the dielectric at x equal d should equal the tangential magnetic field at x equal d at the area. The tangential magnetic field here is B cosine KCD, and the tangential magnetic field in the air is d e to the power minus hd. So here B cosine KCD equals d e to the power minus hd. This is a continuity of hz at x equals d. And it should be noted that the tangential magnetic field here equals the tangential magnetic field here, because we don't have a surface current at the air dielectric interface. If we have a surface current, it would be the difference between the two tangential magnetic field equals the surface current, or the surface current density. Okay? Alright. The other boundary condition at the air dielectric interface is the tangential electric field inside the dielectric at x equal d equals the tangential electric field at the air at x equals d. And the tangential electric field in this case is Ey. So we are going to calculate Ey at x equal d inside the dielectric and at x equal d in the air, and equating the two equations. Ey is proportional to j omega mu over kc squared partial hz by partial x. So it would be minus b kc sine kcx, and this kc would be eliminated with kc squared. It would be minus b sine kcd over kc. On the other side, it would be d over h e to the power minus hd. Now, from the continuity of the electric field and tangential electric field and continuity of the tangential magnetic field, we have two relations between B and D. By dividing these two relations, we can eliminate B and D. So in this case, the relation between Kc and H, it can be obtained as minus Kc cotan KCD equals H. Effectively, this by dividing equation 2 by equation 1. Equation 2 by equation 1. Cosine over sine. And we have 1 over Kc, 1 over 1 over Kc would be Kc. So minus Kc cotan KCD would be 1 over 1 over H would be H. So minus Kc cotan KCD equals H. If you remember, at transverse magnetic mode, it was Kc tan KCD equal H. Here, in the transverse electric mode, it is minus Kc cotan KCD equals H. And already we know from the Helmholtz wave equation, the relation between Kc and H is that Kc squared plus H squared equals epsilon r minus 1 K naught squared. Now, by solving these two relations together, we can obtain the value of the cutoff wave number Kc and the value of H in the free space. In the present case, the function Kc cotan KCD equals H in the KCD plane, HD plane, can be represented as follows. Should be noted here, it doesn't start from 0. So at the value Kc equals 0, the value of cotan is infinity. But the limit that Kc multiplied by cotan Kc, effectively cosine or cotan KCD can be represented as cosine over sine. And here we have KCD over sine KCD. The limit of KCD over or x over sine x at x is 0 is unity and cosine is unity. So at the value KCD equals 0, this value is unity. And in this case, this 1 equal HD. So if Kc equals 0, HD equal 1. Alright? And then we are going to draw the function KCD, cotan KCD. So this is a function cotan KCD, cotan KCD. And as I mentioned, the value of x cotan x is even function. So the function of x is the same as the function of minus x. And this will be 0 when KCD equal pi over 2. At KCD equal pi over 2, the cotan is 0. And it would be infinity at KCD equal pi, and so on. Okay. Now the other function is the circle. Kc squared plus h squared equals epsilon r minus k naught squared will be represented as a circle in the KCD plane, HD plane, with a radius of square root epsilon r minus 1 k naught d. As we said in the case of the transverse magnetic mode, the intersection between this circle and this function would correspond to the roots of the value of Kc and h. And also, we said that the value of h cannot be negative, because we are assuming that the wave above the dielectric interface is proportional to e to the power minus hx. So if h is negative, e to the power minus negative value multiplied by x is proportional e to the power positive x, which is increasing to infinity as x tends to infinity. So the value of h must be positive. So the solutions with h is negative correspond to improper solutions or invalid solutions, as the value of the circle epsilon square root epsilon r k naught d increases, and effectively it increases by increasing the frequency, because the value of d is constant, the value of epsilon r is constant. So by increasing the value of k naught, the value of this radius increases until it reaches to be intersecting with the function minus KCD cotan KCD equals h at positive h values. This corresponds to the cutoff wave number of the transverse electric surface wave mode. So the first transverse electric surface wave mode will propagate when the value square root epsilon r minus 1 k naught d would be pi over 2 or greater than pi over 2. This means that the cutoff frequency of the surface wave modes, of the transverse electric surface wave modes, is given by 2n minus 1 c over 4d square root epsilon r minus 1, where n equals 1, 2, 3, and so on. How it comes? Actually, let us start with the first one. The first one is square root epsilon r minus 1 k naught d equals pi over 2. This is the first cutoff frequency. And here k naught is 2 pi f over c. So 2 pi f over c multiplied by d multiplied by this square root equals pi over 2. Right? Pi over 2, it can be represented as 2 multiplied by 1 minus 1 over 2 pi. 2 minus 1. 2 minus 1 is 1. Over 2, so 1 over 2 multiplied by pi. Okay? Here we have 2 pi. The pi can be eliminated with this pi. And we have 2 here. And already we have 2 here. So it would be 4. 1 over 4 d square root epsilon r minus 1. And this 2 pi f, already we have finished 2 pi f over c. So this is c. So this was 2 multiplied by 1 minus 1 over 4. So 2n minus 1 over 4 c over d square root epsilon r minus 1. If we are going to take the following transverse electric mode, would be after 3 pi over 2. So instead of 1 should be 3. 2 multiplied by 2 would be 4 minus 1 would be 3 pi over 2, and the remaining is the same. So the cutoff frequency for the TEN mode is F cutoff is 2n minus 1c over 4d square root epsilon r minus 1, where n equals 1, 2, 3, and so on. Now by combining the cutoff frequencies for the transverse magnetic N mode and the cutoff frequency for the transverse electric N mode, for the transverse magnetic N mode, the cutoff frequency is NC over 2D square root epsilon r minus 1, where N equals 0, 1, 2, 3, or so on. Or in other words, we can say it is 2N over 4. Okay? On the other hand, the cutoff frequency for the TEN modes is 2N minus 1 C over 4D square root epsilon r minus 1, but N here starts from 1. So the first cutoff frequency, it would be TM0. The following one, it would be TE1. Then the following one would be TM1. Then TE2. TM2, and so on. So the order of propagating transverse magnetic and transverse electric modes is TM0, TE1, TM1, TE2, TM2, and so on. As an example, before the example, the field components now for the transverse electric surface wave modes, they can be represented completely in terms of the coefficient B. So in this case, for x greater than 0 and less than d, it is b cosine kcx e to the power minus j beta z. Here, this was the value of d, and we have already proved that the relation between d and b is that d equals minus b multiplied by h over kc sine kcd e to the power hd. So we can replace any d by this combination. So the value of b, sorry, no, I'm sorry. The value of the relation between b and d equals b cosine kcd multiplied by e to the power hd. d equals b cosine kcd multiplied by e to the power hd. So we are saying that here d, b cosine kcd multiplied e to the power hd and the remaining part e to the power minus hx e to the power minus j beta z. Here this is the value of the longitudinal magnetic field. The transverse magnetic field Hx is given by partial Hz by partial x multiplied by g beta over kc squared. So we can obtain Hx for x greater than 0 and less than d as the derivative here with respect to x would be minus cosine minus sine minus kc sine kcx, and already we have minus here, so kc over kc squared, this would be eliminated, would be 1 over kc. In a similar way, here it would be the derivative with respect to x, so it would be e to the power minus hx minus d, it would be multiplied by h, we have h here and we have 1 over h squared minus j beta b cosine kcd, which is the coefficient, e to the power minus h x e to the power minus g beta z. In a similar way, we can obtain the transverse electric field EY. EY would be proportional to minus j omega mu over kc squared partial hz by partial x. By getting the derivatives, we can obtain the magnetic field at x greater than 0 and less than d. And in a similar way, we can obtain the electric field EY at x greater than d and less than infinity. As an example, it is required to calculate and plot the propagation constant for the first 3 propagating surface wave modes of ground dielectric slab with epsilon r 2.25, and the value of d over lambda is range from 0 to 1.12. In this case, the first mode is transverse magnetic zero mode. The cutoff frequency is 0. So regardless the value of dy over lambda naught starts from dy over lambda naught equal 0. For the transverse electric 1 mode, the cutoff wave number equals c over 4d square root epsilon r minus 1, which was already 2n minus 1 multiplied by c over d over 4d, and here n equal 1, so it is 1 over 4d. By applying f by getting d here and c here, so this is d multiplied by fc over c, so this is d over lambda naught. Lambda naught is c over f, so t over lambda would be 1 over 4 square root epsilon r minus 1. We have put d here and c here, so this is d over lambda naught. D over lambda naught in this case equals 1 over 4 square root epsilon r minus 1. So the cutoff frequency in this value, by applying the value of epsilon r 2.55, we can find that d over lambda naught is nearly 0.2. Okay? The cutoff wave number of TM1 mode, the cutoff frequency Fc, would be c over 2d square root epsilon r minus 1, which was originally n over 2d nc over 2d square root epsilon r minus 1, and n here is 1. So in this case, d multiplied by fc over c, or d over lambda, is 1 over 2 square root epsilon r minus 1 by applying epsilon r 2.25. So the value of d over lambda is 0.4. So the cutoff frequency of the first mode is 0, or d over lambda equals 0. The cutoff wave number of the second mode will occur when d equal lambda over over lambda equal 0.2. The third mode, or TM1 mode, will occur when d over lambda equal 0.4. So from this we see that as the thickness of the dielectric slab increases, we have higher order surface wave modes. So we prefer to use the dielectric slab such that it support only TM0 mode, because TM0 mode already have zero cut frequency. So we are preferring to use this slab between 0 to 0.2 lambda. So the maximum thickness of the dielectric slab in the present case is 0.2 lambda node, such that we have only one surface wave mode in this case. Okay, here as a function of d over lambda, we can draw the value of beta over k naught for the different modes, and it can be noted that the value of beta, or the limit for the value of beta, is the square root of epsilon r. So as the frequency increases, because d over lambda naught here means that this axis increasing the frequency. As the frequency increases, or as the thickness of the dielectric medium increases, the propagation constant inside, or the propagation constant of the surface wave mode, has the limit of the propagation constant of the dielectric slab itself. Okay. Actually, the concept of surface wave modes has a very important application in microstrip antennas and microstrip lines, and the coupling between microstrip lines. So we are going to discuss the effect of these surface wave modes more deeply when we are going to discuss microstrip antennas. All right.